All right, so hopefully I haven't scared everybody off by using the words chi-squareds and all these weird tables and all that kind of good stuff. So, because obviously it gets scarier as we go into this page as well. So, I'm just teasing. It's not actually that bad. It just does look kind of bad at times. So, all right. So, how do we actually calculate our? So this just kind of summarizes some of the M&M data, and you're actually going to use this as one of your examples later on. So our test statistic is going to be the chi-squared is a sum of the observed minus the expected value, all divided by the expected value in this case. And to kind of simplify it a little bit, we can change observed and expected to just O and E and stuff like that. And so what we're going to do, we'll need to calculate that and the alpha level to figure out exactly where this guy falls. And so again, just a little hint on what the p-value looks like again. And so again, we're going to use that chi-squared distribution as a way to calculate our p-value after we've calculated our test statistic. So in this case, this is just a summary of what we're doing. So the testing of the goodness of fit model. So again, we're basically just trying to see, does the data that we have sort of look like a chi-squared curve? Like that's really the idea. So are these two things similar or are they different? So, or do they match the expected frequency or do they not match the expected frequencies? So in this case, so again, like I talked about earlier, the data is going to be broken up into categories. So our degrees of freedom are based on those categories. So in above, there's 6 colors of M&M. So these would be our categories, these guys here. And so this would be our observed values. So what we want to look at is our degrees of freedom is just going to be k minus 1 for these guys. So for the above M&M example, our degrees of freedom would just be 5. So now this is also where it gets kind of nice. So even though some stuff is a little bit tricky, the hypothesis part, the state the hypothesis is pretty much a piece of cake, because whenever we're doing testing the goodness of fit, the goal is we're trying to see whether this distribution fits or matches the frequency or does not. So pretty much this is always going to be what the H naught and the H1 look like. And we also don't have to worry about less than, greater than, and all that kind of stuff with a chi-squared, because it's always going to be greater than. So you don't even have to check it. And that's another thing I forgot that you don't even have to worry about. So the null hypothesis is always going to be the observed frequencies match the expected frequencies. So again, this would be like an equal situation, even though we're not writing it that way. And H1, the observed frequencies do not match the expected frequencies. Now, you will word it in such a way so that it relates back to the original problem, but it's always going to be that situation. So either the frequencies match or the frequencies do not match. So that's kind of one of the nice things. So again, the test statistic, we just talked about that. So I'll show you how to calculate that because that can be a little bit tricky. So I'll show you a couple different ways that you can do it. Calculating our p-value. So again, we're going to be using the chi-squared CDF value after we've already used our test statistic to kind of compare the alpha level. And I talked about how we find the alpha level. And again, the alpha level, just like the t, we're going to have to find that every single problem because the degrees of freedom are going to change every single problem. So just because we find one alpha level, it's not necessarily going to be the same for every problem because the degrees of freedom are going to change. And then finally, draw a conclusion, just like before. So the good thing is steps 1 through 4 are all the same. It's just how we get there is a little bit different. All right. So in this case, what we've got is our example 1. We've got work absences. Manager wants to know which days of the week her employees are absent in a 5-day work week. Most employers would like to believe that the employees are absent equally during the week. So in this case, that's kind of a hint. So she tracked down the next 60 absences and recorded on which day they occurred, and the results are shown in the table below. Do the absence occur with equal frequencies during the work week in this case? So in this case, state the hypothesis. So our H naught, remember what we're looking for is the observed frequencies match the expected frequencies. So what that means is that the expected absences, match the observed absences. So basically, you're equally likely to miss a day. Like most people aren't going to take off Friday or something like that. That's really what that's saying. So H1 is going to be the expected absences. Do not match the observed in this case. So again, just like always, we always want to put what we want to prove in H1. So we always have to word it in such a way that that's what we're trying to prove, because we can never prove H naught is true. So even in this situation, the best we can do is we can, fail to reject H naught, which means that we can't determine whether the absences match or not. We can't say that they do match or anything. All right, so to kind of help calculate the test statistic, what I've done is I've kind of written a table to kind of show, because ultimately if we go back to what the formula looks like, so let me write it down here just to remind you. So it's going to be the sum of all the observed minus expected values squared divided by the expected values, or expected absences or whatever. So first we have to figure out, well, how in the world do we even figure out what the expected absences are? Well, the goal is, since we expect them to be equal, what you would do is take the total number of absences and add them up first. So, and I think it said it was 60, but I should check, I guess, just to make sure. So 30, 42, oops. Yep, so 60, good. And then what we're doing is, if we're assuming that they're exactly the same, so in this case we've got 5 days of the week, then what we would do is take 5 divided by 60 and then put each of those absences for those days. So that's what the expected is. Since we expect it to be an equal amount, just divide 5 into 60. So in this case, we'd expect these absences to be 12 every day. And so we can kind of see by looking at it that that's obviously not the case, because Monday and Friday, it looks like more people seem to take off. Wednesday and Thursday seem like less people take off. And Tuesday seems about the expected value takes off. So now down below, that's where we want to fill in this part of the chart. So the expected values or expected frequencies, you're always going to have to calculate. They're never going to be given. So kind of keep that in mind. So that's another kind of tricky part to these problems, is you always get the observed, but we're always going to have to figure out what the expected is. So there's always going to be some kind of a trick like I did there to figure out what the expected absences are. All right. So now what we want to do is subtract across, so observed minus expected. So in this case, 15 minus 2 equals 3. 12 minus 12 equals 0. 9 minus 12 equals negative 3. 9 minus 12 equals negative 3 again. And then 15 minus 12 equals 3. All right. And so notice the next step is, after we subtract them, we want to square each of these. So if you want, you could just do this at the end. So I could do O minus E squared. Because the goal is, we don't want to have negatives in there, because if we get negatives, it's going to end up canceling things out. So we want the variability to be positive, so we need to square it. So in this case, 3 squared would be 9. 0 squared is 0. Negative 3 squared is 9. Negative 3 squared is 9. 3 squared is 9. So now we've calculated the whole top part. So now what we want to do is sum all these guys together and divide it by the expected absences in this case. So what we're looking at is, we're going to have 9 over 12 plus 0 over 12 plus another 9 over 12 plus a 9 over 12, 3 9 over 12s. Good. And so in this case, all the denominators are equal, so we can just add straight across. So we've got 4 9s is 36, and 12 just stays the same. So 12 goes into 36 3 times, so we can see that our chi-squared test statistic is 3 in this case. All right. So again, that's not a very big number. So graphic wise, like it's probably going to fall somewhere in here, would be my guess. So, because the numbers on the right tend to be fairly big. Oh, I forgot to do the alpha level first. I should have done the alpha table thing first. Ah, dummy. All right, well, I'll go back and do that now after I've already tortured you with the expected value. So in this case, I've got my alpha is 0.05. My degrees of freedom, so I've got 5 days. So my degrees of freedom are going to be 4. So I need to go and find that chi-squared alpha level so I can see how it kind of compares to the 3 that we have here, just to get an idea of when, also to see what part of this chi-squared graph we're going to shade in. So in this case, now I need to go to my table. So let me pull up the whole table here. Whoops. Oh, chi-squared distribution table. So I gave you up to 40. I don't think we'll ever need a degrees of freedom up to 40. At least I hope not. But if you know, but hopefully they're all smaller than that. So again, we've got the same alpha level of 0.05. Our degrees of freedom were 4. So that tells us that our chi-squared score for an alpha level of 0.05 is going to be 9.488. So what that means is, when we go back to our little packet here and we shade in, so I'm going to shade in just say this part here. So this is my alpha equals 0.05, and this was 9.488. So remember again, so this is my reject H naught, everything over here is going to be my fail to reject H naught. So just looking at this and knowing this is our test statistic, what do you think? Are we going to reject H naught, fail to reject H naught? So hopefully everybody's screaming out, fail to reject H naught. I agree. I think that's going to be what's going to happen in this case. But let's check it just to make sure. So what we want to do is do our chi-squared CDF. So our 3 is our lower value. 100,000 is going to be our upper value. And then our degrees of freedom is 4. So let's go to the calculator real quick here. So again, we go to second vars. So chi-squared CDF looks to be 8. So again, put 3, comma 100,000, comma 4 for our degrees of freedom. And we end up with a p-value of 0.56 in this case, which doesn't sound very promising at all. So our p-value equals 0.56. And so in this case, 0.56 is clearly bigger than alpha. So again, so our test statistic kind of went along with what we were proving up there. So in this case, since our p-value is bigger than alpha, then we fail reject H naught. There isn't sufficient. To prove that the expected and observed match. So there isn't sufficient evidence to prove session. Let's prove observed match in this case. All right, so I've got a bunch here for you guys to try. So again, same kind of idea here. So we've got practice 1. So this one, the percentage does give you the idea of what the expected is going to be. So what you'll do is once you calculate your frequency, total those together. then you're going to multiply those by the percentage to get your expected in this case. So it's a slightly different trick than the one I did, but if you have the percentages, that's a nice one to use also. So we've got a practice 2, casino gaming. So with this one, you'll have to use the binomial distribution to actually calculate the expected probabilities. So, but we know how to do that. Hopefully we remember. This will be good practice for the tests and stuff. And then here's the M&M problem that we were recreating above. And if you remember, this is data that I'd shared with you guys early on in the semester when we were doing probabilities. And at that point in time, we couldn't actually prove that the probabilities differed, but now we actually have enough tools that we can actually prove whether the probabilities are the same or don't match at all, which is kind of nice. So kind of nice that we've learned a lot of stuff along the way. And then here's a little false fire alarm, and when do students do homework, and I think that's it. So try these, guys. Let me know if you have any questions or anything like that. I'll be around all day in case you get stuck. And otherwise, when you're done with that, come on back and check out the 11.3 video.